Good? We good? Okay, hi everyone. I'm Becky and this is Joe. And the research topic that we're interested in is the use of convolutional neural networks to recognize and classify images of coins. And so to understand the inspiration and thinking process behind our problem, I'll go over a brief introduction on these two categories. The representation of the coins is to be learned in training based on supervised learning approach, which is when the neural network is provided the known inputs and outputs, and then the function is developed that can replicate these known observed values. And we'll try to mimic the way humans perceive the world around them through layered architecture of neurons in the brain. And we call this the convolutional neural network. And it's extremely useful in pattern detection and image analysis.
Okay, so why coin identification? Well, as a supervised learning problem, classifying objects is something that's been looked at before, but usually only for relatively more simple things, and for coin grading, usually this picture should be in more detail. Coin grading is a lot more difficult to do as an image classification problem because you have to just look at a whole much larger variety of details that vary very, very slightly, but have a big difference from an overall grade of the coin. So like things that can in fact affect a coin's grading are things like its strike, its preservation, luster, attractiveness. These are all inherently subjective quantities, but we do have a lot of data of graded coins that we could pull from. So it should be possible to train a convolutional neural network to do so. This problem is valuable from the standpoint of one, it's something that currently only humans can do. So if we can make a machine do that, that's pretty valuable in itself. But two, if we can make a network that can actually identify which because of the minute changes in coins from wear, luster, from these things, that's actually a pretty valuable image classification problem itself, just that level of detail. To my knowledge, I don't think anybody's really tackled something of this type before, so that's basically our problem.
So prior works that we referenced throughout research are listed here. We go over, or we consider results and methods from cases where CNNs are used to identify not just coins, but images of different categories and even handwritten messages. And so we consider these just to see how different factors like depth and layer and amount of training involved to see the impact on the network performance.
So basically, what other people have done in this type of things, they've been able to identify like this is a quarter, this is a penny, this is a nickel. Some people might even say this is a quarter, it was minted in this year, maybe it has this mint mark. Nobody's actually gone through the full grading process like I said before. We want to bridge that. We want to actually create a subjective model or a quantitative model for grading a coin and have a machine actually be able to learn.
So again, the main approach is to design a convolutional neural network by specifying different filters in each layer that can detect these patterns. And we consider patterns as simple as edges and corners, and patterns as sophisticated as full faces and full objects. And so we have these convolutional layers, and steps that would follow are normalization to emphasize what's really the most relevant parts, regularization to prevent overfitting, and probability conversion to help us decide or to make the final decision. And the specific data collection that we'll be using are the images of coins at different rotations and flips.
So that's just the projects we want to learn and improve our course. What type of filter should we actually use when we have a picture of a coin? What type of features do we clean up? Usually the convolutional neural network, the goal is to try and reduce your parameter size by kind of grouping things together. But for something like coin grading, you can't always do that because every bit of the coin is important for its overall grade. So how do we find a way to kind of replicate or have a convolutional neural network that doesn't have as much as weight savings to kind of define a convolutional neural network? This is an interesting problem. And also, how much data do we actually need to train it? I mean, is 10,000 examples of graded coins enough? Like that could be doable. Is 100,000? That might be a little harder to get, but maybe that data exists. 1 million? I don't know if that data exists. So, I mean, how much data do we actually need? And then we'll also hope to find a way of making a number of these different networks and using the type of ensemble selection to pick the best one based on some type of majority vote. And then the hardest challenge will, of course, be the grading process in itself. So our goals, short-term goals, just to be able to do what people have done before, just identify a coin, this is a penny, this is a quarter, then, this is the year it was minted, this is its mint mark, if it has one, maybe it had, and then maybe, is it dirty, is it not? And then the long-term goal would be a full, grading of the coins.
Any questions? Do you see both sides of the coin?
How this would work is you have to actually have two pictures for each coin, the front and the back. Maybe even a third of the edges themselves. So, yeah.
Okay. I'm Carl, and I'm going to do a project on how we can learn control barrier functions to provide safety guarantees in reinforcement learning. And this is a project together with Richard Cheng, although he's not enrolled in the course. So if we want to use reinforcement learning on physical systems, safety critical systems, such as robots or self-driving cars or something similar, we're likely to explore some unsafe region of the state space as we try to search for an optimal policy. So safe reinforcement learning is trying to address that issue by giving some safety guarantee during the learning process. So Richard recently presented a paper at AAAI which combines a model-free reinforcement learning-based controller with a model-based control barrier function-based controller. So what it allows us to do is, in the picture on the right here, if we have the RL algorithm propose some control action, we have some way of determining if that control action is safe, and if it's not, we can project that control action into a region of safe policies. And then we can continue the search for an optimal policy around that safe controller rather than around the unsafe controller. So a key assumption in this work is that we had access to this set of safe controllers, or a safe set that is valid. And these sets are in general for, especially if you're taking control bounds and if you have a nonlinear dynamical system, they're very hard to compute. So what we propose to do is to explore if we can use machine learning methods to try to solve this problem of finding this safe set. So if we have a dynamical system with some known dynamics, F and G, if you can see it, and some unknown dynamics D, we consider a setting where we have a nominal model and an initial safe set associated with that model, and that we have some high-level safety specification. So if we take an example of the inverted pendulum, we can have a high-level safety specification, which is we want to stay within a certain interval in terms of the angle. And then that high-level specification has implications for the other states of the system. So if we have the angle on the x-axis and the angular velocity on the y-axis, if we want to ensure that we stay within that safe set, we can't have a angular velocity bringing the system out of the safe set when we're close to the boundary. So we need to have some non-positive angular velocity when we're close to the angle boundary. So the question is, how can we compute that implied constraint on the space of angular velocities based on the high-level safety specification? So yeah, so we'll have something like this where we have a safe region in green and the unsafe regions in red. So these types of problems in control are typically solved by Hamilton-Jacobi-based methods with some kind of reachability analysis. And the problem with those is if we have nonlinear systems, it very quickly gets very hard to compute. So we're highlighting two papers here which are one from Aaron Ames' lab here and one from Berkeley. And both of them are essentially using Hamilton-Jacobi-based methods to try to compute this safe set. And then they propose some approximations to deal with nonlinear systems. But the issue is that their approximations lead to very conservative safe sets. So you're restricting the actions that the agent can take a lot, which lead to suboptimal policies. So yeah, as I've said, we're then proposing to try to use some machine learning method to learn this set of reachable states instead. So some very early preliminary solution ideas are, one is to, if we have this initial safe set, we can explore data in that region still being safe. And then we can use that data and try to learn some estimator that says that from the states we've seen, what states were we able to reach. And then if we have that estimator, we can start from the high-level safety specification and kind of back-propagate to get the constraints on the other states of the system. So that's the main method we're looking at. Something else you could do is to feedback linearize the system and try to do the reachability analysis on a linearized model, and then try to transform back to the nonlinear model. And the final one is that you can sample points around your existing safe set and then try to simulate the system if it can reach back to your current safe set. But as this is a machine learning project, we'll mainly focus on number one. So I think the main challenge will be this balance between being too conservative but still being able to prove guarantees about the set you're learning. So the goals are, one, to try to demonstrate that ML methods can be used for these kind of problems with some provable guarantee, and want to validate the methods on simulation in this project. Any questions?
Our project is about using machine learning tools to figure out, understand, learn, and characterize aggregate flexibility for deferrable levels. So nowadays we're facing a higher and higher level of renewable energy penetration, and as you may see from this figure, in California, the number of installed PV devices has increased over years. renewable energy is not always a good thing, because the deep renewable energy penetration has created many operational challenges, and therefore it causes many troubles. The darker shown here is one of the famous examples in smart grid. That's mainly because the imbalance of timing between the energy production and the peak demand for the electricity. For example, solar energy is only available during daytime, but the peak level of demand often occurs in the evening when everyone goes home. So. So meantime, deferred loads like electric vehicles, they also raise many questions. For example, how to design a scheduling policy so you can basically specify each driver's demand, and you can charge their cars and so on. As one of the one of the possible solutions to solve the darker problem, workplace EV charging is one of the solutions. For example, the idea is I can charge my car during working time so that I can basically feel the value of the darker, and partially maybe also reduce the peak demand because I may not need to charge my car at home. So our group has built an EV charging station, and this photo is taken in the gym garage. It's not so clear to see here, but so we have started collecting data since last year. So basically, what we can get from the data is like this information. We have the arrival time, departure time, and energy delivered, and the bounds for the charging rates for each charging session. And we have done some basic statistics for the data. For example, you can see like during weekdays, basically each user, they arrive at 8 or 9 a.m. and they leave around afternoon sometime. But during weekends, the behavior is different. So the data we collect contains two parts. One is the user claim data. Basically, we have user labels for that part of data. And the other part is the data is unclaimed because we only force user to use the mobile app since that's the member. So we only have that part of data which is labeled. Okay, so now let's move on to the problem.
Okay, so the aggregate flexibility problem can be described in this following scenario that each EV will arrive following some certain distributions, and they will provide some flexibility, such as the energy they need and when they will depart. And then, based on this demand and flexibility, the aggregator will calculate the aggregate flexibility and provide it to the power grid. After this power grid receives the aggregate flexibility from all the aggregators, it will compute some optimal power dispatch and will send some certain control signals to each aggregator. And they will ask this aggregator to follow this control signal. And then the aggregator will allocate the power based on some power scheduling policies. So as you can see, there are two main problems in this framework. The first one is to define some suitable notion of the aggregate flexibility. By suitable, I mean it should reflect this flexibility, and also it's easy to compute since we need to do it in real time. And the second problem is to design a real-time scheduling policy. It also needs to be computationally easy and also achieve some optimality in some sense. So there are already some studies on this aggregate flexibility. For example, the first reference proposed to emulate a battery given the system dynamics to measure the aggregate flexibility. And another work provides some theoretical analysis in this framework and also propose a priority-driven power allocation policy. But we are thinking about a data-driven method might be better because once we understand this data distribution, we might design better notion of this flexibility, and we can have better design of this allocation policy. So we have some initial ideas. We want to, for this aggregate flexibility, there are some theories like we can use the set theory or some polytope or some upper and lower bounds. And we are thinking about to estimate this data distribution based on the GMM or some density estimation framework in the machine learning. And to design the power scheduling, we are thinking about to use some multi-arm bandits or some idea from the reinforcement learning. So the short-term goal is to take advantage of data so that we can better propose and validate our theories. And the long-term goal is to apply this to this real system in the Caltech garage. Any questions?
Bijan and I are going to talk about the problem of covariate shift and some strategies to mitigate it. First, I'll define covariate shift. So the definition we're working with is when you have a target distribution and a source distribution, and the causal relationships among the model variables differ between these two distributions. The setting we're thinking about is we train a model on the source distribution, we want to apply it to the target distribution. And because of the changes in the apparent causal relationships between the model variables, our model doesn't generalize well, or doesn't apply well, at least in this particular target domain. So we consider two joint distributions between covariates x, which we'll represent by x, and labeling or whatever parameter we want to predict in terms of the y. We train a model, which we notate with f of x and then parameterized by w, so linear classifier or something. We're training it in a supervised fashion from data sampled from our source distribution. And we want to use it to make predictions in the target domain. But as I just described, because the distribution of the covariates in this target domain is different from the distribution of the covariates in the source domain on which the model was trained, we expect that the model will break or not generalize well. And we'd like to understand how to train our model in such a way that it generalizes well to the target distribution. We're kind of operating under the assumption, so kind of a neat thing to do would just to be, if we had supervised labeled points in our target distribution, we just like put all the data into one data set and then train the model on that, and then we'd have generalization over both the source and the target domain. We're operating on the assumption that it's expensive to do that, that labeling new points is difficult. So like, I think if we train like a disease classifier or something in some city in the US, we want to apply it to like a country in Africa, for example, where the data might not be well labeled or might not be as extensive, but gaining these supervised labels is difficult. So we're kind of assuming that it's difficult to kind of train to add new labels in our target setting. Okay, so basically what we want to understand is if we were to add some points to our source distribution from our target distribution, what would those be? How do we pick the key data points to improve our model generalization performance while relabeling or labeling the minimum number of points from the target distribution? So here's just kind of a formal description of what I just said. So we take some subset x nu from our covariates in our target distribution, and we want to minimize the loss over our target domain of the model that's now been trained over the union of these two sets of the subset x nu from the target domain and or all of the original source data. And for this new union of covariates, we assume we have labels for everything. So believe it or not, this problem has been studied before because it comes up a lot. And the naive thing to do is just importance weighting. So basically we want to make our target distribution, our source distribution on which we're training the model look as much like the target distribution as possible, and we just reweight the frequencies of the points. So that's that p target of xi over p source of xi. We're just reweighting the loss calculation by the observed frequencies of points. A more sophisticated approach is especially this kind of naive importance weighting breaks down in the higher dimensions. It doesn't describe the difference between the two distributions very well, so you can use something like KL divergence to kind of minimize this difference between the target and source distribution to compute your importance weights in a more intelligent fashion. And then there's another approach which kind of is in the spirit of looking at all the data together and somehow minimizing a loss over all of that. But it's not exact, it's not relying on every point being labeled, but looking at the differences between the covariates and the two distributions. So Babija will now talk about some of the ideas we have that differ.
Yeah, so like Luke said, we're going to not necessarily try to reweight points that we already have. We want to figure out, okay, points where the model now might break. And one of the issues with reweighting points we already have is that we're probably going to be weighting points that are not occurring very often. So by adding the weights, you're essentially amplifying the noise. So we're going to try to change our perspective a little bit and think about, okay, what can go wrong when you take a model trained in one domain and move it to another. So the insight we have is that clusters of highly correlated variables, it's hard to know which variable in that cluster is actually causing y to change. So, if you're trying to predict y and x1 affects causes y, you could have latched onto some x2, which is highly correlated with x1, and now when you go into a new domain, those two variables become independent. Now you're not predicting anything because you didn't actually latch onto the correct variable. So this is kind of an illustration of what can happen, right? If x1 is this like light green variable here, that's the actual cause of y. We could have picked any of the variables or a combination of them all in this cluster. These are all things highly correlated with x1. And we could have created a classifier based on that. Now once we go to a target domain, maybe this cluster splits into two different clusters. So now x2 and x3 are, as a group, maybe they're still correlated with each other because they're in a cluster, but now they're independent from x1, x4, x5. So if our classifier had learned to predict y based on x2 or x3, we would have had an incorrect classifier in the target domain. our insight here is that, you might say, okay, well, one solution is to compute Pearl causality, if any of you know what that is, or try to learn the whole causal structure, learn that X1 is the cause. But that's going to require a ton of data, because now we need to know all the interactions between X1, X2, all those pairwise interactions. And what we realize is we actually don't need that full information. All we need is the interaction between these two new clusters. So whenever a cluster breaks, all we need to know is, okay, what happens when that whole cluster, green cluster is 1, and this whole red cluster is 0, and the flipped case. Because what we've been seeing before is only these all being 1 together, these all being 0 together. So the points to consider would be 0, 1, 1, 0, 0, and 1, 0, 0, 1, 1. So that would that's kind of our intuition for points to choose when adapting our model. So we're hoping to kind of use this clustering idea to develop some theory and then test that on data that we've kind of generated from a Bayesian network. So our goals are, like I said, to first try to come up with a theoretical bound on the performance of taking a classifier and moving it to a new domain. Once we have that, we can try to reason about, okay, which points will change that bound the most, so that we can greedily choose points that will improve our classifier for the new domain and resolve the imbalances. And then we're also going to potentially look into other metrics for distances between distributions, like Wasserstein distance. Finally, this is getting more into long-term goals. Maybe there's a way to also make models more robust to changing their domains, rather than having to add more data points. Any questions?
Thank you.
Hey guys, my name is Ishan, and my project is going to be on domain adaptation with the neural rendering model. So just as a brief introduction, successful computer vision today oftentimes relies on very massive annotated data sets that are oftentimes costly to collect and costly to label. And without this high quality data, or without a lot of it, it often leads to poor generalization despite recent advances in neural network architectures. So one solution that has been attempted is to train models on synthetic data. However, that hasn't been found to perform well because of latent differences between real and synthetic data, the real data that being the data you infer on, as you could probably see up there in the top right corner. And tackling this problem of differences between training and test distributions is known as domain adaptation. There are two main cases we see in this. One is covariate shift, which was just talked about, when the the source distribution and the target distribution are different, but the labels are the same. And label shift is when, conversely, the labels are different between the distributions, but the general distribution of the covariates are the same. And so my focus will be on covariate shift in a semi-supervised learning situation. So one proposed solution that could potentially solve this problem are deep rendering generative adversarial networks, or DRGANs. And what these do is they combine neural learning models, which are a generative model that essentially mimic convolutional neural networks at inference time, but are generally unable to produce realistic images due to a lot of additional latent variables. And if you put that in a generative adversarial framework, it's possible that this framework will allow the network to learn or to optimize which latent variables to weight, and thereby generate the most realistic looking images that can then align with our target distribution and allow us to train on the best images possible. And so the nice thing about this solution is that if it were to work, it can become applicable to almost any computer vision problem in which you need large data sets. Right? In the semi-supervised learning, you can now have some real images, some images that are generated by this DRGAN, and thereby perform well on training test distribution regardless. And so my goal for this project is to first establish a working model. There's a lot of code out there, and I can kind of use that to just get a baseline measurement of how to perform. The second part is to prove feasibility in a new domain. And I've been working with this company part-time that's doing street intersection analytics. So I plan on using street intersection data and vehicle data to see if we can produce realistic images of street intersections, which can vary widely across the continental US. And so ideally, by solving this problem, I could help them solve the problem of what is essentially a very costly data collection process. And finally, to kind of further the research for DRGANs, I'd like to define and test an alternative to adversarial loss that works better for the neural rendering model and for the general problem space. Ideally one that can take the geometry of the data into account, that can better understand the latent variables, or can maybe even work with temporal timescales, as I have video data of these intersections. And so, just as some preliminaries, there are relevant data sets, and there's a lot of, like I said, a lot of different applications for this, so a lot of data sets I could use and test this out on. There are numerous papers establishing feasibility and code, so at least as a baseline, I can set up the problem and move from there. And this is my general schedule and my references. Any questions?
Thank you.
Hi everyone, I'm Bochi and this is Porta, and today we are going to talk about our project, optimization on GANs. So GAN is a particular example of competitive optimization, which is optimization paradigm where we aim to solve a min-max problem. So it's basically a two-agent setting where two players are playing a zero-sum game, and one is to minimize the loss function, and the other is to maximize that loss function. So it's an important topic in machine learning optimization and even game theory, but our knowledge towards solving a competitive optimization problem is limited, and so particularly in the convergence behaviors. So we will focus on the particular example of competitive optimization, namely the GANs. And in a GAN, there are two neural networks, the generator and the discriminator. So the generator generates some candidates such as fake images that resemble real-world images, and the discriminator will evaluate or differentiate the real and fake images. And so it's effectively like solving a min-max problem with the loss function characterizing how similar the real and fake images are. So we can look at the conceptual figure. We can see that there is a generator, and it will learn to generate a distribution of images that mimic the real distribution of images. And the discriminator will learn to classify these real and fake images. So a main challenge of training GANs is that it will not necessarily converge to local notch equilibrium points. And often we use simultaneous gradient descent ascent method to solve a min-max problem, but a gradient descent ascent method may not converge to good local extreme points. And moreover, it is proven that in some cases, it never converges to local notch equilibrium points.
So there are modified algorithms in order to overcome this problem. So one proposed algorithm is the optimistic simultaneous stochastic gradient descent ascent algorithm. This is the same algorithm we see in this class. So basically, the optimistic assumption is about the previous gradients, and if you assume that the gradients are the same, they should give the same update rule as in the classical gradient descent algorithm. However, this is an optimistic assumption in general, and therefore the dynamics of the system changes. So, due to the change of the dynamic, the points that this optimistic gradient descent algorithm changes, and under some assumptions, it is proven that the local minimum maximum point is a subset of gradient descent stable points, and this set is also the subset of optimistic version of the gradient descent stable points. And this is a visualization. So here we see that this point is gradient descent stable. This point is OJDA stable, and this point is the real local minimum maximum point. And if we run gradient descent algorithm for this function, we see that some of the times the algorithm converges this point and this point, and for the OJDA case, the algorithm may converge this point, and this point as well. Therefore, it seems that the OJDA algorithm is worse than GDA algorithm. However, this does not mean that OJDA is useless, because the previous result is true under some assumptions like invertibility of Hessian. An example where the Hessian is not invertible, GDA may fail to converge to the stable point, to the Nash equilibrium. However, OJDA will converge to the Nash equilibrium in that case. There is another algorithm called TTUR, 2 times scale update rule. In this case, we take the learning rates for the generator and the discriminator different, and it's seen that the algorithm converge better local minimum maximum points. So we propose to combine OJDA algorithm with TTUR, which is not found in the work. In the previous works. Also, one of our aims is to differentiate good and bad equilibrium points experimentally. This is the main challenge of this project. We will probably not provide a theoretical background, however, we will try to understand the characteristics of the equilibrium points by doing extensive simulations. And in general, gradient estimations are noisy, and we can investigate the robustness of the algorithms to the noise, which is also not done in the previous works. Also, there are distribution of GANs such as Wasserstein GANs or the BC GANs. and they have different loss functions that may give, for example, differentiation characteristics and, for example, different Jacobian eigenvalue characteristics. Therefore, algorithms will probably work different. From the implementation perspective, training of GANs are computationally intensive, so we should work on cloud servers such as Google Cloud or AWS. And we have source code from the previous work, and we will also reuse that code to, in the first step, reproduce the results in the papers, and also by modifying them, you want to investigate the characteristics of the local Nash equilibriums. These are the references. Thank you.
Yeah, so I'm going to talk about what we call competitive gradient descent, which is a new method to solve minimax problems, as we talked about just before. So yeah, minimax optimization. First in this sort of like abstract framework, it just means we have some function depending on the two variables, and we're interested in finding sort of maximum minimal points, maximum one, minimal the other one, and the other variable. And this models two-player zero-sum games, and in particular it models generative adversarial networks, or at least on an abstract level. And as you have just heard, there's the naive approach, is just, I do, like, one of the players just goes to the direction of greatest descent, the other goes to the direction of the greatest ascent. That's the maybe most straightforward way. The problem with this is this. We sort of, we apply this method even to a simple function like x transpose y, and we see this spiraling behavior. And that is really, what happens is that the players are not taking into account each other's action. And what this means is that, for example, here, if this is the x-axis and this is the y-axis, here it might be good for x, which wants to minimize things, to move to the right, but then it becomes good for y, which wants to maximize things, to move to the top. And once y is positive, it becomes the better option for x to move to the left again, to become negative. because X wants the product to be negative, Y wants it to be positive. And so that's really the thing where it happens when you play rock, paper, scissors, right? You always think, what does the other player think that I do, that they do, and so on and so on. And the simultaneous gradient ascent doesn't take this into account at all, and that's the reason why we see its behavior. And that causes troubles in training GANs, and so that's why I think it's a valuable problem to look into. And yeah, there are two main branches maybe of dealing with these kind of problems, and sweet, it's optimism and consensus. So with optimism, basically, so these are ways in which we can say how do we model this taking into account the other player's action. And the first sort of modeling assumption we can do is optimism. We assume that the other player, essentially it means we assume that the other player plays the same strategy as they played the last round. And then we do the right thing for that strategy. The other option is consensus. So we actually change the optimization problem in order to reward people, so reward the two players for agreeing and converging towards something. But we all know, so optimism and consensus, that's not how the world works. And in particular, that's not how zero-sum games work. So the question is, can we get the competition back into these algorithms? And what I think is maybe an interesting analogy is to start with ordinary gradient descent just for the minimization problem, which we can think of as we have some sort of global nonlinear optimization problem, and the way our players solve it is they take a linearized version, so a very simple sort of model of this optimization problem, and they determine the next step by solving this optimization problem together with some quadratic penalty that basically penalizes them for moving too far. So that's why this is one of the step size. So we take this local simplified model of the true problem, we try to solve it, and we penalize us for trusting this model too much by penalizing us for moving too far away from the point where the model is valid.
One question. So I noticed that the Y player doesn't appear at all in this aspect.
Yeah, that will come right now. So that's just for minimization.
Okay.
That's by analogy. And so now the question is, we could call this thing a game, that is then a single-player game, sort of local approximation of the true single-player game. And so what is a good sort of two-player game that would be a local approximation of a global game that the players are playing? And of course, in some sense, without this term in the middle, this this non-zero sum game is the game that is being played by this gradient descent ascent. But the problem is that this game doesn't have any sort of connection between the variables of the two players, so it leads to the spiraling behavior. And so the idea is that now if we include the off-diagonal block of a Hessian, so the block that modeled the sort of lowest order interaction between the two players, we could modify this game and now say this is the sort of local approximation of the underlying game that the two players are playing, where each player is penalized for moving too far away because neither of the players has reason to trust this model arbitrarily. And so we see here player, but now because of this off-diagonal term of the Hessian, these players are coupled. So somehow what player X thinks that player Y might play influence what player X plays, and so on and so on. And so the idea is we could use the strategic equilibrium of this game as updates for our descent. And indeed one can show, it's a simple exercise, that this game has a unique strategic equilibrium, which is also pure, which means that it's not randomized. And I mean, this is just a simple taking derivative and setting it to 0. But this is somehow, from this game theoretic integration, somehow something meaningful to do for these two players, I believe. And then basically one plugs this in and one gets a closed form solution for this sort of strategic equilibrium. And the suggestion is to use this as an update set.
But before you just get that, this is an algorithm you're proposing from scratch. Is that right?
Yes. As far as I know.
Okay, of course.
Yes, and so the first question is how to prove theoretical convergence results for the algorithm, and at least in the convex-concave case, under some sort of smoothness, sometimes one can get something, but the question is how will train on the world, and so on. Does the method work in practice? So I mean, it does seem to do something half reasonable, sort of low-dimensional, like polynomial or something like that, but the question is, of course, does it do something reasonable in GANs? So the plan is to just use some of these like example GANs from the Python tutorials and just try to plug this algorithm in a new optimizer. And also, what are ways to make it scalable? Because in some sense, at some point in order to determine these updates, that we need to invert these type of matrices, which somehow which really correspond to this resolving, at least on the linear level, this what does the other player think that I play, that they play, and so on. And so of course the idea, and then the idea is like, how do we do this in practice? So we might, for example, for small step size, because this is regularized with the identity depending on step size, for small step sizes it might be just fine to do iterative methods, maybe low-rank approximations of the hashing. So that's something one has to see in practice. And then finally, how does it compare to optimism and consensus? And in some sense, the update rules are somewhat similar, but what essentially the novel ingredient is really this additional term. But basically what this says in a like game theoretic point of view is that it says that if the reason I'm playing this is basically if I play some strategy, how vulnerable is this strategy to the other player changing their mind? That is really what this additional factor does, that it sort of it urges me to rather choose strategies that are robust to the other player's actions, as opposed to just the strategies I would get from optimism or from consensus. Yeah, does that help? That's, I guess, the question. Yeah, that's it.
I'm Sophie and this is Vita, and we're working with our mentor Ken on active learning for a deep convolutional neural network. So, as we know, CNNs are often used in deep learning, especially with supervised prediction of images. But to have supervised learning, we need a really large data set, which can be expensive to annotate. And what we want to do is reduce the number of labels using active learning. So prior approaches, previously we've seen active learning using uncertainty sampling, likelihood and density weighted models. Uncertainty sampling is better for refining like classification boundaries, while likelihood is good for finding new classifications within the data. Density weighted models basically take those two previous approaches and also weight it by how representative the unlabeled data is in the unlabeled pool. And this is usually measured using similarity. We've also seen likelihood functions of generative networks such as the variational autoencoder, flow-based models, and pixel CNN to not be reliable. And what I mean by unreliable is that, for example, in this diagram here, when the flow-based model was trained on fashion MNIST, it returned a higher likelihood for the data in MNIST rather than both the training and testing data in the fashion MNIST. So this might be a problem that we will face. So we want to use the neural rendering model, which is basically like a reverse version of a CNN, and we want to use the inference of that to use as our CNN. So here's the general diagram of our approach. So we're going to take our labeled data, we're going to train the NRM, and from our NRM we can obtain the likelihood using the reconstruction loss. We also want to implement some function for uncertainty and similarity, and we want to query, choose which point to query based on a function that takes into account all three of these measures. And in the end, after training, we want to use this process called JMAP, which is basically the inference to convert our NRM into like a CNN and use that for image classification.
Okay, so as mentioned in our approach, we basically want to get a good estimation for the likelihood, uncertainty, and similarity of our data set. So first, we need to make sure that our NRM model we plan to use is reliable to give us the likelihood of our data set. So as mentioned before in some previous research, people have shown that deep generative neural network doesn't really give you the reliable likelihood. For example, when the data set is trained on some data, is trained on CFAR 10, it might give a higher likelihood for the data set from SVHN. So we want to make sure like NRM, or we want to modify NRM to let it give us a reliable likelihood of our data points. And then we need to decide what is a good measure of uncertainty and similarity. So for uncertainty, conventionally, people will calculate uncertainty based on P of y given x, which is the output of the softmax layer. But this might suffer from overconfidence or incorrectness. So instead, we were able to use some approach called Bayesian neural network to calculate the P of omega given x, where omega is a latent variable in your neural networks, and use this as a measurement of our data set. And as for similarity, typically people will just calculate the distance between different data points in your unlabeled pool. But because we want to use our CNN for image classification, this approach might be super expensive for us. So we might need to pre-train a neural network to perform the similarity measurement task. And after we decide on the model for each measurements, then we will incorporate the three criteria into some query function to enable us to query the unlabeled data. And we have some initial results on testing the reliability of the NRM model, and it turns out it suffers from the same problem as other deep generative neural networks. So if we train the neural networks using CFR10, so you can see the negative log likelihood for the trained data is pretty low, which is nice. But when we test it using our using CFR10, some data point from CFR10, we haven't been used those data points for training and used some data points from SHVN, which is another data set. You can see the model actually gives higher likelihood for SHVN rather than CFR10, which is the data set we trained this model on. And this is some unsupervised, semi-supervised training because we didn't use all the labels from CFR10 dataset. So if we use all the 50K labels from CFR10 dataset, we still observe like this model gives higher likelihood for SHVN dataset rather than CFR10. Same if we just change the number of labeled dataset, number of labels and unlabeled data points, we observe something similar. So I guess our short-term goal is first we need to obtain a reliable model and give us a likelihood, uncertainty, and similarity, and incorporate them into our query function. And our long-term goal, if we really can find those models, we can incorporate those models in our active learning settings and reduce the number of data points we need for CNN without sacrificing its prediction accuracy. So these are the references. Questions?
Thank you.
Last but not least.
Definitely least. All right, so there are reasons not connecting. Why is it not displaying?
Is there any other connector?
What? It's connected through HDMI.
Can you use other converters? Maybe a Thunderbolt or something.
No, I don't know Thunderbolt. Is this the right? Is this the right one? The focus one? Okay, cool. So my presentation is about generating adversarial points. So when I actually first started this project, I didn't even know what an adversarial point was. And when I started doing it, I realized that one of the big problems I was encountering was exactly this. So after doing a lot more research, I realized there's a lot of connection between my initial kind of like project abstract idea and this. And here I'm going to kind of bridge the connection. So in this presentation, I'm going to kind of turn a little upside down. I'm going to explain what adversarial points are first, and then how my kind of initial idea applies to them. So first of all, adversarial points are not to be confused with generative adversarial models. The term adversarial kind of means two different things here. In the GAMs, right, like as a lot of people in this class presented about, adversarial is kind of used to mean two competing neural networks, right? Here, adversarial simply means like erroneous or like incorrect points. So okay, yeah. So ooh, can't really read that. So I'll just explain to you what it is. So none of you guys can read this, huh?
So maybe with the light switch. Maybe the light switch.
All right, yeah, that should be good enough. So here are kind of the three main leaders in adversarial points, or at least as far as I would see. So there's Szegedi is the guy who kind of first brought them up, or is at least credited for it. The idea behind an adversarial, so yeah, not to be, so here's some references. I should kind of said this at first. So anyway, so the idea behind an adversarial point is it's a kind of input vector to your model that really just does not look like the thing you're looking for, but it convinces the model that it like is in fact what it's looking for. It can be seen as like hacking the model in a way. Now these points are pretty rare. You have to like engineer them in a specific way for them to exist. But so these guys all kind of, they're all Google guys. They all worked on like actually many papers with this, where they actually propose different methods of generating these points, the meaning of them, and like how to actually use them to our advantage. So here is kind of one example. So here is like this was a very I think this was ImageNet or something that's like a very advanced like modern neural network trained to detect a bunch of stuff. Yeah.
Sorry, do we have a class yet? No.
It finishes in 2 minutes.
I'll be really
2
quick.
minutes?
2 minutes, yeah.
Okay.
Anyway, so this is an example of an adversarial point. The idea is you can like, this image is clearly appended to the human eye, but it was engineered to convince the network that it's something else. The way they do it in a lot of ways is gradient ascenting the input against the output probability. And you can actually make a very minimal change to your original input to completely drastically like engineer a difference in your output. So this is important because, well, this is kind of a lot. Here's another example. Here's a bunch of examples. This was like for, yeah, so also notice these examples are all like very different. Like different things can like trigger this response, which is one of the things I'm going to investigate. And so importance, it's kind of a lot of things that they kind of give us a little bit of insight onto like what neural networks actually perceive in the images. This is an issue that we need to handle for generative models. One of the things that I'm very interested in is as cybersecurity kind of goes more and more towards machine learning models, you know, predicting like kind of behaviors and things, understanding how this works allows like for kind of a new generation of hackers to like start hacking machine learning cybersecurity features. So I think it's pretty cool. I think it's important to start talking about. And I mean, discussions have already been happening, so this is kind of why I'm interested in it. So this is actually an adversarial point I generated myself for cracking the MNIST. This one does actually better than 50% of the actual testing images. So yeah, this convinced the neural network that it's seeing a 1 when there's clearly not a 1. And the probability score if you take softmax was like 99.9 or something. And this is really simple. I just did gradient ascent on the input image. So meaning you keep the weights fixed. You don't touch the model. You just like see how your how changed in your input. Change your output, and yeah, you just do gradient ascent step by step. It took me like 2 tries to get this happening. So for me, it seems kind of interesting, kind of scary, pretty cool. So yeah, kind of a lot of short-term goals here.
that are research oriented. I want to kind of figure out this like adversarial point kind of manifold. Obviously I can't, like, it's going to be a hard problem to tackle, but I think it'd be kind of cool to look into like how it's shaped, how it relates to like data points, things like that. Just gonna hurry up here. And yeah, long-term goals. So this is actually what the original project was about. I wanted to maybe say, okay, normally we take kind of gradient descent of the output with respect to the input, but what if we kind of hop in a layer in the middle? Maybe we're able to generate kind of different adversarial points that could give us some new information. That's basically it.